And will be my pleasure to be your chair in this session. The first presentation is from Sebastian from BMW. He will introduce us the Spider project that has been hosted a lot of years in BMW. Sebastian, the floor is yours.
Thank you very much. Good morning. Hi. My name is Sebastian. I'm with the Department for Driving Simulation and with the Driving Simulation Center at BMW for about 2.5 years now. It's actually my third time at this conference, and today, the first time I have the pleasure to actually share something with the community. Today's talk will be about Spider, which is our own in-house development of a driving simulation software. So, before I get started, let's watch a small video.
Pop, pop, la 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 la.
So, I guess your first question will be, why do I show you this video? As it obviously is not about software, but it's about a message. And I think the actor conveyed that pretty well. The message is something BMW stands for and hopefully will always stand for in the future, and that's sheer driving pleasure. But sheer driving pleasure itself is something which you feel when driving a car. When it's done, you can assess it only at the end. But what we want to do is convey sheer driving pleasure already through the development cycle. So, today's talk will first of all go into detail why we made a hard decision to make our driving simulation software our own, make it in-house, despite there being so many awesome solutions out there. Secondly, we'll share some design decisions and architecture overviews about our software today, followed by some stories what we already managed to achieve using our own in-house developments and what we are planning to do next. So, in order to understand what the drive of innovation is made of, we go a little bit over a very classical, very oversimplified development workflow of a vehicle, or for any product, so to say. So, at the beginning, you have a concept, which is something that normally doesn't exist outside of papers and PowerPoint slides. You do a concept evaluation and you assess if this is something your customer could benefit from in the future. You do your validation, you start with coding some bits and pieces of your product in software, do a component development, get some hardware done, hardware in the loop testing, until you ultimately have some prototype you can actually bring to the road, first test track, then the real road, until you ultimately can bring your product to release. Within the automotive industry, this is usually a 7-year cycle. But from today's perspective, where innovation accelerates and the thrive to innovation grows, there are problems with that cycle, which are obvious. So first of all, you can see it on the top. Customers are only involved at the ultimate end with such a product development cycle. So if you do in your concept phase something that the customer ultimately doesn't want to buy, it takes very long time to reiterate on that problem, even a whole product cycle, and damage is already done. Other than that, at least from our perspective, this lacks agility. Everyone who has worked in an agile software development environment so far knows as soon as hardware gets into the loop, things get slow. Hardware doesn't fit quite well into agile development. So let's modify it a little. The key thing is we want to front-load development. Front-loading from this expensive hardware-driven testing into the downwards-facing software-driven testing branch. And that can, of course, that's why we are all here, only done by simulation. And what comes with that is not only digitalization, it comes an increase in agility, and also our customer can be included right at the start, already in the concept phase for customer acceptance tests and also safety in the use tests. So what we ultimately want, we want a workflow that is agile, proactive, reacting before damage is done, use case driven, and customer centric. And this leads me to Spider, our in-house developed simulation framework. But we don't see it as a simulation framework. We see it more or less as an integration platform, and that's where we offset cost. Spider in itself is just a framework, as it said, and it puts all together the pieces that are developed across the company to make up a full BMW driving experience. For example, to experience something, you need the auditive part. So that's why we use the same electric sound design engine that actually drives the electric sounds in our cars. And by using that, we can also do rapidly small modifications and get right to the real thing with our customers. Overarching to the kinesthetic experience, vibration and vertical dynamics are made and specifically tuned by the colleagues that do it on the test track all the day. Ultimately coming to driving dynamics in the kinesthetic experience. We use the same models in our simulation that are used when parameterizing vehicles before even the first prototype exists. Last year, Joost Van Rooij presented something about multi-body simulation, which is currently the standard and works very well. The next big topic is the functional experience, advanced driving assistance systems. We not only want to include what's actually in the cars, how it works for our driving experience, but we also want to make it really easy to have our concept at a low-code level integrated into driving simulations and have the interactions assessed by our customers. The last part, the visual experience. For that matter, we work closely together with our design departments, both providing us with UI UX designs and the actual models of future cars, so we can convert CAD models right into simulation models and have them play in our simulation. So, but how is it done? The program is ultimately called Spider. Spider stands for Software Programming Interface for Distributed Real-Time Driving Simulation. Yeah, we had to jump some hoops to get to this abbreviation, of course. But as the name says, Spider on its lowest level is a framework for enabling simulation. It does not simulate on its own. For a simulation to work, it needs modules, and modules can be expanded by plugins to do something. So what is Spider made of? On every machine you run Spider, there is a service. The service is called NetServer. NetServer is deeply integrated with the operation system, the Linux kernel, which it runs on. And it takes all the overhead which is coming with communication, data management, starting, stopping modules, garbage collection, resource management, and stuff like that, so that a module developer doesn't have to deal with this stuff. Also, Spider isn't only designed to run on a single computer. We, of course, want to go to the cluster. And that's where NetServer also comes into place. NetServer alleviates all the workload that is necessary to do cluster communication and the management of the modules across as many computers as you want. But a very big topic when it comes to simulation is the management of data. Usually in simulation, there's a lot of data that has to be moved around, not only within a computer, but also outside. That's why there's a second service that ships with Spider, which is the data pool server. The data pool server acts kind of a central management unit for a publisher-subscriber-based data communication flow. The data pool server ensures that every module has the data it needs at the right time. Within a computer, this works over shared memory, which is, of course, the most resource-friendly and fastest thing. And over the network, we do it with UDP multicast. It's also designed to do these intelligently. So for example, in this here, the second computer, computer B, doesn't need a dataset X, so it's not copied over to avoid unnecessary network traffic. But we also want event-driven simulation workflow. That's why we have two additional layers of communication, which are the events and named values. Both of them can be used to trigger something throughout the simulation, for example, something that happens when a traffic light turns from red to orange and green, and so on. And we have named values, which are parameters which seldomly change. And those are only sent at changes. So there's an additional method how these can communicate. So let's look at a small example how a minimal simulation setup involving a real simulator could look like. It's minimal, but it works. So in this example, we have two computers. Going back to our BMW driving experience we want to achieve, we have some modules in there which actually are heavily developed together with other departments at BMW, which is, for example, the sound engine with electric sound design plugin for simulating electric vehicles. ADAS functions. In this example, we have a level 3 function for testing with our customers put in the simulation. Simulation car, already mentioned, driving dynamics, multi-body simulation from the driving dynamics department, and the UI and UX designs right onto the prototypic screens in the mockup. But Spider also ships with a lot of default modules that are essential for a simulation, which is, of course, a central graphical user interface, more to that later, a bird overview for the operator, mockup interfacing, the graphics engine, motion queuing is also an in-house development. Not only the algorithms are designed to work throughout our whole 14 simulator fleet, but also the safety precautions are put inside that. And of course, some additional stuff like platform interfacing, protocolling, and traffic simulation, which Jens Brauer presented yesterday, available right in the module. Considering that we need a lot of additional computers for the image generation, as much as 20 computers are commonly used to participate in one single simulation on a simulator. So that's about the framework. Now we go to design decisions. So one topic that always comes to mind when designing a simulation is the trade-off between a low latency design and a deterministic design. So when you have a study where the human is in the loop, determinism is not a hard requirement because humans are not deterministic by default. But if you want to conduct, for example, CI tests with your simulation or automated assessments of driving functions, determinism is key. So, of course, you could switch from a low latency scheme as shown on the left, where every module and every process schedules itself, works asynchronously, and ensures minimal latency because data is used as available. There's also a drawback with that. It might reuse data. For example, if here the process isn't finished already, it reuses the data in the second process from the previous step. That's a low latency approach. Determinism, on the other hand, requires an outside clock to be scheduled. All processes start at the same time, which ensures perfect data lineage because a data set calculated here is always used in the next step. But there could be overflows, and those overflows spread across the whole scene. Yeah, and we have also one complete cycle in simulation latency. So, of course, we can switch between both, depending on what Spider is used for. But for online simulations, we actually did a lot of brainstorming and came up with something additionally. So why not both? And that's called mostly deterministic scheduled execution. And there we define subchains of a simulation that benefit from determinism. For example, the workflow from simulating vehicle up to the platform controls fed by the motion queuing can run in a deterministic manner, while they are still scheduled as a compact element on the outside with an asynchronous low latency optimized scheme. So let's look about the GUI. There are also some interesting design decisions made there. The first one is obvious. We want a central GUI. one interface that controls everything. As I've said previously, there are up to 20 computers involved in a single simulation, and you want to have one screen, one keyboard, and one mouse to control them all. Also, this GUI needs to be customizable. On the one hand, it needs to provide every option to control the last centimeter of every simulation. On the other hand, it also needs to be easy to use for an end user, an operator as we call him, who has nothing to do with programming a simulation, who is there to operate throughout all the studies. That's why we have a flow approach, as you can see above. And ultimately, when you are done with developing, you end up with a simple GUI, which is customizable. You can put widgets, plots, and stuff like that on there, which is necessary for operation only. And one special thing, which speaks for an in-house development, is the feedback loop. We want to be agile. It's all done with continuous integration and continuous development. And when the user has feedback or encounters bugs, with the press of a button up here, you send a 60-second complete time history with all the data available directly to one of our developers who can reproduce your issue in a complete and deterministic way and solve your issue, preferably within minutes or within the same day. And he's also able to put his solution from his working place directly on the simulator and tell the operator to just restart the application. We are done. Couldn't get any faster there. So currently, we also have a proprietary scenario language, which is called Motion. We are constantly monitoring the market for standardized solutions. So Open Scenario DSL is actually a quite good candidate that we could switch in the near future. But we have our requirements, and that's why we made the decision. Usually in our simulations, we have hour-long drives with very complex scenarios, event-based triggerings, and hundreds of entities. And to make that work, we need a template system, because reworking all these hundreds of entities need to define what they do is a lot of work. We have a graphical user editor where you can put templates together and design your hour-long scenario within minutes. On the other hand, also the scenario language is currently human readable, which makes bug fixing at the simulator easy. The graphics engine is also an in-house production at the moment, based on Unreal Engine 5.3, as it seems to be the common sense across the community. It supports OpenDrive and NDS as a road system, and it's also tile-based, which complements the approach seen prior with the motion language. So you can put tiles together, you put scene templates together, and get your simulation going within a few hours. It's of course a multi-channel system, as our simulators normally consist of not one screen, but up to 16. It works with modern technology such as NVIDIA Mosaic and Video Card Sync to achieve that. We support both artificial and real roads that were measured with laser scanners while driving over them. And we use the open standard open simulation interface to communicate with our graphics engine. So, what could be achieved using an own driving simulation? So, one big use case is driving dynamics. Driving dynamics is something that really relies on realistic depiction of driving and the vehicle. So, some milestones we had in the recent years were the introduction of multi-body vehicle models, so models that simulate a 700-degree of freedom model within a millisecond sample time in real time. And therefore, we can achieve a cueing realism up to 20 hertz. For example, in vertical dynamics, as shown on the right in the scenario, 10 to 20 hertz tends to be the range where vertical dynamics can be best accessed. And a few months ago, we achieved that our colleagues who do this normally on the test track, that's a real test, it's near Munich, decided that they can ultimately lay off their testing for most of the part into our simulators. So there goes suspension development. Tire development is done since more than 2 years now on our simulators. Comfort assessments with our customers. and straight line acceleration performance testing. We did an interesting one where we just tested with customers how much acceleration is actually considered performant and when it gets uncomfortable. Because as we all know, electric cars can do a little bit more than petrol cars. So the next use case, a very big one, ADAS, Advanced Driving Assistance Systems. Here the simulation milestones are we are able to produce scenarios with hundreds of entities. Jens mentioned last year it takes a single core to simulate 100 of them. We can have simulations with 1 hour plus in length. And with a recent study with over 100 participants, we managed to get down to a motion sickness rates of one of our biggest simulators of 3%. So very usable data at the end. At the company, this is already used for assessing and prototyping level 3 to 5 driving functions, of course, safety of the intended functionality assessment, and customer acceptance assessment. Or watching back to the V model, we can do that in front now. Last, UI UX, it's a big topic. In the last years, we more and more use actual VR goggles in our simulation for virtual and also augmented reality. We tried combining big simulators with VR goggles and had also good results with that. A mixed reality vehicle in the use case is ready to use. We are going to make that available for the company soon. And hardware rapid prototyping is also a big thing. Put a new screen in there, put it in the simulation, let the people drive and feel it right from the start, which enables forward thinking more than 5 years into the future already now. Customer acceptance and safety of intended functionality tests again. So, coming to an end. What's next? Smart agents is a big topic. We have a new PhD. You will probably hear from him in the few upcoming years at this conference. We want to make them even more intelligent, more realistic. A big topic is low friction testing. So our people don't have to go in complete darkness in the winter months to the north of Norway for testing where sun doesn't shine all the day. They can do it in August in Munich and go bathing in the sea later on. And the last thing, mixed reality, a big topic, as you can always see here at the conference too. We want to make that a usable use case so that we can put Spider in the trunk of the car, put on our VR goggles and drive around in a big concrete field without the need of real other drivers. 25 years of development have passed since we started with Spider. I think currently we are on a very good path, but we are always open for discussion at that point. An in-house solution, of course, has its drawbacks. It's costly. It takes a lot of effort to maintain, and there are many solutions out there. So at any time, we are open to talk about mixed solutions. But currently, we are on a big way. We put the drive to innovate into our simulators. We accelerate with our simulation center the development of future vehicles, and we don't plan to stop. We will continue in the future. So, thank you.
Thank you, Sebastian. Thank you.
Any questions?
Any questions?
Yes.
Thanks for the introduction. So, presentation. Sorry. I just want 2 questions. So, the first question is for your ride comfort model. You
Yes.
have a 700 freedom model, so it's a very huge model. In this case, the model is separated in different sub model, or is a global model?
The vehicle dynamics model?
Yeah.
Yeah, that's actually a global model. It's one single model, a 700 degree of freedom multi-body physics simulation model. Unfortunately, I'm not able to go too much into detail with that because that's delivered by our driving department. But from seeing it, it's a single model, but it also requires a really heavy machine to run on. It requires its own machine with 48 cores and real-time certified hardware to be able to run at that speed of a millisecond.
Okay, so
Does that answer your question?
Yeah. So
Okay.
you use multi cores from the simulation.
Mm-hmm.
Okay. Another question is normally for ADAS system, the sampling time is higher than the vehicle model's sampling time.
Mhm.
I don't know, in your case, the ADAS function is simulated with 1 millisecond or 10 millisecond.
ADAS function is sampled at different rates, of course. Yeah, I wouldn't go into detail because of the time with that. As vehicle models and motion queuing and stuff like that, which benefits from high frequencies, are sampled at a millisecond currently. ADAS functions actually are internally sampled again in different sample times. There's 10 milliseconds, 20 milliseconds. Path planning is divided into global path planning and local path planning, which run at different sample rates. They are all over the place, but it's also benefited with an asynchronous communication scheme. Data is used as a way level. You don't run into any real-time problems with that.
Okay, so in this case, how can we match the signals? Because with 10 millisecond or 30 millisecond, the signal is not continuous if we perform some derivations. So I don't know, you apply some filter or some technical tool.
So also depends on if problems arise with that. So that's where mostly deterministic schedule execution comes into place. You could either match the signals by externally scheduling them. So for example, if one runs at 10 milliseconds, the other one at 1, you let it run 10 times and then sync them up. And if systems can't be synced up, I would go into another example. For example, setting your motion queuing signals to the machine that uses them. There often arise, I think, the problems you're mentioning when the signals get out of sync. There we use LLP2 filtering for getting them together again.
Okay, thank you.
Okay.
Thank you, Sebastian. We are running out of time, but I think someone have further questions. You will be available.
I will be here the whole day. Feel free to speak to me.
Thank you again for the